Hello, my name is Paul Brooks from Viavi Solutions. Today I'm going to talk about pluggable coherent optics, specifically the new challenges with interoperability. Interoperability is the key to an open multi-vendor ecosystem, and with DCO, pluggable coherent optics, playing a major role with many new applications, ensuring successful interop at all layers is going to be critical for mass deployment. So coherent optics have played a major role in DCO and transport for many years now, but that's typically been in closed engineering link-based systems. The emergence of pluggable digital coherent optics, the so-called DCO, has led to a more open and multi-vendor ecosystem. And we're now seeing a significant ramp for 400 gig class modules, and they have a broad range of applications, including DCI, as well as classic DWM transport. With this open, multi-vendor ecosystem, demands for seamless interoperability are critical for our successful large-scale deployments. This presentation discusses the range of challenges from the photonic layer through to host module management and performance monitoring that need to be addressed while discussing interop. But first, we'll talk a little bit around what are pluggable digital coherent optics. So let's first look at the evolution of coherent optics. Coherent optics have been around quite some time in optical transport, but that's really been based on line card systems in a closed engineered system from a single vendor, where that single vendor did all the integration of both ends and of the complete photonic link. We've now moved to a more open ecosystem based on commodity DSP and optics, underpinned by variety of standards coming from organizations, including the IEEE and the OIF. This has allowed up many new applications and has opened up the multi-vendor interop challenges. Of course, those very high performance DWM line cards still exist, and they have many unique applications, but pluggable coherent optics with their price and density expectations open up many new applications which we hope will be very successful. There's two main application spaces we see today for pluggable DCO optics. The first is very much along the lines of a classic DWM, typically based around a 400 gig CFP2 DCO carrying multi-services over long reaches out to 1,000 kilometers. Multi-services, Ethernet, of course, is a very common, but we also see OTN, FlexC, and other services, and carrying those over a classic DWM transport system with line side reaches of 1,000 kilometers or more, typically based around the CFP2 form factor. The second application space is much more around new applications, and this is including such areas as DCI interconnect. Typically here, we're talking about shorter reaches, but higher density pluggable optics with a much more aggressive price expectation. And a clear example of this is the QSFP DD 400 gig ZR. The main focus is Ethernet services. Of course, this may also be brought in to include FlexC, but the main focus really is efficiently carrying Ethernet services 80 kilometers, in some cases a bit more. There are varieties of ZR, ZR plus, etc. But no, the ZR application space generally is focused around in these sort of applications. And again, to meet the price, density expectations, the form factor of choice there is really what the typical client slots are. So QSFP DD 400 gig ZR is a clear application there. If we were to open up a pluggable coherent optic, we basically see two major functional blocks: a photonic block, that's very, very much highly integrated. Terms like silicon photonics, integrated optics are often closely associated with these applications. And we have a DSP electronic block. These are the two main function blocks. Of course, many other things go in to make a pluggable DCO module, but these are the two main spaces. So the photonic area is really, as it name suggests, is really focusing on the photonic management and processing of the signals. So the input is typically going in via a polarizing beam splitter into two hybrids, where the signal is mixed with a local oscillator. That's a local laser tuned approximately to the same frequency, and then goes into photodetectors, which are detecting, due to both polarization states, the in-phase and quadrature signal. And this might have some filtering, some amplification, and in turn is then fed into very, very fast A to Ds. And then a digital signal processing will do all the rest of the signal processing needs to extract the signal in this case. If we look at the block diagram of DCO much more in a system view, we can look at it this way. Photonic block interfaces the optical line side. Then in the middle, we have the DSP, including the framing, the soft decision FEC, and all the other functionality there. And then we have the interface. And the interface to the host side has three main areas. The data interface, okay, and that's the higher layer protocols, FEC, OTN, Ethernet. We can think of the interface also in terms of electrical, the PHY layer, the parametrics, the skew, other things associated with the electrical fast signaling. And of course, critically underpinning this all is the management interface, which does the module management, module setup, and of course also the performance monitoring reporting as well. So the electrical host side is another major part of how we view the DCO module and how we look at Inter-op as well. And of course, finally, all this is wrapped in an environmental sense. So you must think in terms of environmental, power, cooling, and the mechanical aspects as well. So it's the three, if you like, things that all need to come together just to bring up the module, just to to really have it interoperating at the most basic level. So before we dive deeper into Inter-op, let's define what Inter-op really means. So in simple terms, Inter-op means the DCO module under consideration has to operate with the desired host, switch, router, or other piece of network elements, and of course with other optical vendors modules on the photonic side. So a module from one vendor could be plugged into a third-party host, switch, or router. And then on the photonic side, could be talking to an optical module of the same class, but supplied by a different vendor, and perhaps plugged into a different manufacturer's host at the far end. So we have the host Inter-op, that's the slot the DCO fits into. At the very basic physics layer, we have the power and cooling. We then have the electrical, the PHY layer, the signal integrity, and the high-speed, signals going to and from the module, making sure that the Inter-op at that layer, the data formats. So it's not just Ethernet. We may also have multi-protocols, but make sure that all the formatting, data structure, data signal is compatible. And then critically underpinning all of it is the module management and control. To both the host and the module work together seamlessly, can the module be successfully orchestrated and integrated into the host system. On the photonic Inter-op side, we think of photonic parameters, we think of the modulation, we think of the performance monitoring. All of these must work together. So for Inter-op, we have the host Inter-op side, that's the slot the DCO fits into, and we have the photonic Inter-op side, that's the photonic link and the module at the far end, which may be from a different vendor. So Inter-op themes. The first area, of course, is the photonic layer. This is the main area people consider when we talk about Inter-op. Really, this is how the conversation starts with Inter-op. In reality, it works very well. There's been lots of good work done in the standards organizations when the IC companies and the module vendors have really been diligent here. They've, the standards have been robust, clearly defined, and a lot of expertise in the IC companies and the module vendors to make sure this area has been really addressed. Of course, it doesn't mean it's problem-free, but lots of work's gone into making this work very well. On the host side, the first thing we touch is the data layer. The DCO optical module has to work with a range of clients. Ethernet really is a very typical one they all must work with, but then there's other multi-services as well. We see from the higher performance CFP2, this includes OTN and Flexo. And with such services, OTN and Flexo, there is many varieties of how those clients can be encoded. OTL, FOIC, etc., all can be possible candidates for multi-service. So it's important that the interpretation of that in the module, the management in the module, is compatible with what the host is desiring. So this includes things like FEC and map implementations are consistent, as well as the alarm and error management. The module management. So close orchestration is needed between the host and the DCO module via that module management interface. It can be MDO for the CFP2 or seamless with the Coherent extensions typically used today on those QSFP DDs. Now all of those are on the auspices of the OIF, but subtle differences, interpretations can lead to challenges. And of course, there is lots and lots of things you need to manage on that module, lots of setups with the DSP, with the module host interface, and that really needs a lot of diligent work. This is very complex, real-time, interactive software and firmware existing on the host and on the module. A lot of care must be taken together, and not just under normal operating conditions, but especially under alarms and errors, to make sure that the module and the host understand what's going on and how to recover from alarm errors and other anomalous conditions. And again, we'll explore that a little bit later. Performance monitoring, well, that's a very big deal. The modules really need to report a large number of photonic parameters at a system level. These can include the optical parameters, optical signal noise ratio, PMD, and of course data information as well. Prefect BER is a very well one. That needs to be done seamlessly, quickly. Often the host wants to pull off large amounts of data in real time as part of its own network management and network visibility. So that data must be reported correctly. And of course, it's important in the multi-vendor ecosystem that different vendors' modules report the data in a consistent manner. If a module at one end is giving one OSNR, a module at another end is giving a very different OSNR, that can lead to problems. Which module do you trust? Are you sure that network will behave correctly, especially when we start going back into fallback conditions? So that needs to be something really addressed as part of that inter-op theme. Photonic inter-op, well, we are using complex photonic modulation. DP-QPSK or 16 QAM are typical choices for some of the modulation we see at 100 gig and 400 gig. They're clearly defined parameters, and organizations, including the OIF and the IEEE, and very good engagement across the whole ecosystem has really helped it. It's not a major headache. The expertise that exists in these IC companies, module companies, just really address this very well. Now, of course, it's important to make sure that under stress conditions, under real-world conditions, not the perfect lab signal, but when we have real optical links with disturbers, with rapid changes in polarization, optical signal noise, that this photonic interop still works. So we at Viavi recommend using our MAP product portfolio to allow very precise and calibrated photonic disturbers to be used to ensure that photonic interop is going on correctly and it works under the full range of conditions expected in an operational system. The module management MAS, well, that's actually a very, very big area. Even today, with the 400 gig and 800 gig client optics, we've seen the module management interfaced and the host orchestration of modules actually being a major challenge. This is far more complex than pluggable coherent optics. They have far more operating modes and, of course, far more optical parameters and system parameters that must be reported seamlessly integrated into the host. So that DCO module, don't think of it just really simply as a pluggable optical module. It's actually an integrated DWM system, including those complex photonics, DSP, framers, host interfaces, and management. All of this really must be seamlessly integrated into the host network element, and that's done via the serial management interface. Real-time events must be managed quickly, while generating housekeeping activities must also be supervised. So that host to module interface has to carry these things out and also react very, very quickly. This is a significant challenge that involves that tight integration. Module firmware, software, host management software, all have to work hand in glove. And it's not just a steady state, but also real-time events, loss of optical signal, host interface squelching, frequency variation, remote alarms and errors are just some of the examples that management interface must manage and correctly report up and down as the data is coming from the module flowing into the host module. Actions might be taken, reconfiguration may be occurring in the module. So all that happens over that interface and has to happen seamlessly without modules getting stuck or software getting locked up. There is a large range of parameters that need to be module. In fact, if we just follow the signal flow from the photonic layer through to the host interface, there's several areas where there's lots of information needs to be pulled off. As we start in at the photonic layer, there's the loss of signal, of course, and there's the hard loss of signal where the photodetector is detecting no light. But there's also software generated in the DSP loss of signal, looking at how that's been recovered. There's the data clock recovery. That's all done via software and DSP nowadays. There's dispersion compensation, CD and PMD compensation. Again, that's a very important parameter to track. They need to be reported. And of course, polarization, that can track at kilorads per second, the ability to accurately report that and track that over the interface. As we move through the DSP, error vector magnitude, optical signal to noise ratio. Then we go into the digital layer, the soft decision FEC. We'll have pre-FEC BER, we'll have post-FEC errors. All this, again, the alarms and errors need to be rippling through that management interface. And of course, on the host interface, the electrical interface between the module and the host, that needs to be managed and controlled as well, whether it's going into squelch states or released and recovery of signals, all need to be closely orchestrated and accurately reported over that interface. And this is one of the most significant challenges today in interoperability, because the range and breadth and complexity of the firmware that must exist on the module and seamlessly interoperate with what exists on the host, that's very, very critical. So we at Viavi have worked very, very hard. We've realized the challenges that have grown really from 400 gig client optics, and we now see with the pluggable DCO optics. And I think the key thing that really helps work on interoperability is an integrated environment. So we at Viavi have created an integrated environment in terms of all the different layers you need to manage and control in our ONT 800 product family. We've provided integrated support for pluggable DCO optical modules, and this environment includes all the things like power and cooling, but also includes native electrical I/O, physical layer management, all the protocols and traffic from Ethernet and multi-services, all underpinned and orchestrated by management tools, module management, whether it's over CMIS or MDIO, backed up by triggers and visibility of all the different layers. It's really bringing together the high-speed host interface that goes over the electrical interface with the right protocols, Ethernet, OTN, while managing the physical layer and orchestrating it all over the CMOS and MDIO tools. They can't really be separate. You really need an integrated applications that really are context aware of what the data traffic is, whether it's Ethernet or OTN, what's it doing, and then what's the module doing at the same time. Trying to pull together separate tools for I2C debugging for the module while integrating that with third-party traffic generators over other interfaces, that's very, very challenging. Having context-aware applications that have visibility in both the protocol domain, the electrical domain, and the module domain is really critical to understanding what's going on during the host to module interop phase. Let's look at a very, very simple case, which actually can be very, very challenging in terms of interop. And we call this very simply the loss of signal testing. So we may have one vendor's optical module, then of a network, going through an optical link, and then the DUT from vendor B can be inserted in a network element, in this case in a Viavi ONT DCO test set. If we simply interrupt the optical signal from vendor A, what does vendor B report? Does it quickly identify that that channel's gone down? Does it blank out in the correct time? Over its management interface, does it report it's a loss of signal? Does it report correctly what's gone down? Does it squelch the host, or does it go into an unidles pattern? Does all that happen quick enough without giving erroneous information or data over that interface? Then when we bring the vendor A module back up again via an optical switch, like a map solution, does vendor B's module correctly identify the recovered loss of signal? Does it go? How quickly does it recover the signal? How quickly does the framer realign? How quickly does it deassert the squelch and give valid data again? All this has to happen reasonably quickly, has to be orchestrated by that host management interface, and at all times the vendor under test, in this case vendor B, is it correctly reporting what's going on? Is it not going into erroneous states? Worst case, giving error messages where there is no errors, or locking up due to firmware or software incompatibilities, needing manual resetting. So all this, a very simple scenario actually is quite complicated. Another similar example is looking at optical disturbers such as increased optical signal noise ratio. Again, we have a reference signal coming from a third-party module. Using the Viavi map family, we can add disturbers. In this case, we're adding excessive optical signal noise ratio. We can control that very precisely. The module under test, in this case, mounted in the ONT family, again, can be brought up. And then we can, as we change and vary the OSNR, we can watch how the module management interface correctly reports changes in OSNR. When OSNR degrades very badly, do we start seeing alarms and errors being raised by the module as we get close to that FEC limit? If we bring it down again, does the module correctly recover, correctly identify the signals getting better? In worst case, if we make a jump in the optical signal noise ratio, does the module quickly identify that, quickly fall back without giving us erroneous information over the host interface? Is it reporting correctly all the time, the right level of OSNR, the right FEC level? All this can be validated by a combination of the Viavi map and the Viavi ONT. Remember, performance monitoring involves the photonic domain, accurate understanding of disturbers, including dispersion, optical signal noise ratio, signal levels, but also how accurately they're reported on the DUT over the management interface in that context-sensitive manner. So Inter-op is something that we've talked here, about some real-world examples, but in reality, Inter-op actually happens across the whole product lifecycle. Lots of great work is done by the IC and DSP companies developing, their ICs. So during that early DSP phase, there's lots of opportunities for Inter-op testing, validation of the SerDes performance that goes between the host and the module. Is that FEC and protocol IP correct? What's the general performance? So all the way through this Inter-op testing, even before that IC is integrated in the module. When the module's ready and the module's being developed, again, the signal integrity on that host interface is very important. Understanding the errors, the robustness there. What's the performance like? How well are those, is the module set up? That module management and firmware, again, plays a major role. Once the module, is available, it's got to be seamlessly and effectively integrated into network elements. And this is really where the real Inter-op really starts. So network element, host port, the module have to work together seamlessly at the data layer, management layer, at the system layer. So all of this must happen, whether it's over simple structured Ethernet traffic or far more complex OTN traffic. All the alarms and errors that the module reports have to ripple up through that module management interface into the network element and be correctly reported. And of course, this is all context sensitive, whether you're carrying Ethernet or multi-service traffic. As we change, things in the photonic layer, we degrade the optical signal noise ratio. Does the system work as one to identify a degraded link? Does it trigger the right alarms and errors? Is it consistent in the fallback provisioning of a network of a link going down? So as you can see, Inter-op really covers the whole product lifecycle. So in summary, pluggable coherent optics are under development for a wide range of applications. Some of these are very classic applications we've seen before TDM, but many are new and very exciting, which need to scale faster and quicker, and certainly are not coming from one vendor, but involve multi-vendor photonic network equipment from different manufacturers. Inter-op takes place over the whole life cycle, whether it's the first silicon, the module integration, or the network element bring up. And it's well beyond the classic photonic interdomain. Module management, tight integration of that management into the host into the module is one of the biggest challenges for DCO today. It's probably the most significant challenge. It involves very, very complex software and firmware. It's real time, and it's over many, many possibilities because it's different protocols, different alarms and errors, many, many ways these things can interoperate. So the module management and integration of that with the host is critical to successful deployment and interop of DCO. We at Viavi offer a range of solutions for validation and troubleshooting, DCO host side and the Photonic side with our ONT and map products. We also offer a wide range of resources to help all aspects of DCO development, validation, integration. This includes white papers, post stations, and regional application experts versed in the Photonic and host integration and debugging. Please find out more by visiting the following address, viavisolutions.com, where you'll find many, many useful resources to help you get started wherever you are in the pluggable, coherent DCO lifecycle.